It's often the case for a problem like this that the radicand would be in this form a squared plus 2ab plus b squared. Again, I'm talking about the radicand. We're hoping we can fit these entire what, four terms, 1, 2, 3, 4 terms into this form, and maybe there's 4 terms here. It looks like there's 3 terms here. Maybe we could split this up, because if we could, we would get that this is equal to a plus b quantity squared. Okay, and of course you can take the square root of that and get a plus b. And so that's probably the most common algebraic identity for these type of problems. But if you play with this a little bit and try to discover, I couldn't find anything. This is 4 terms, and again, I thought you could combine these maybe to get a 2ab out of it somehow or another, but I couldn't get that to happen. Maybe it can happen. I couldn't get it to happen. So I searched for some other ideas. And so one thing that stands out is that 308, 364, and 572 are all multiples of 4, and I've written that right down here, okay? 308 is 4 times 77, and all the way across you can see 364 is 4 times 91, 572 is 4 times 143. So that looks like some reasonably good news, because you at least can take the square root of 4 out and get a 2 in front of each of these terms. But then you go, well, what next? Well, you just keep writing here, and then it turns out there's another algebraic identity that it's the square of a trinomial that gets the job done here. That's not altogether clear, but if you take a look at this algebraic lifeline, shall we call it, notice that you can assign x to be the square root of 7. Okay, we'll write it right here. X equals square root of 7. Y is equal to the square root of 11. And again, this is not as well a known identity, but it works in this particular case. Okay, and we'll call z square root of 13. Like that, folks. And so, under those assignments, x squared would be 7, y squared would be 11, and of course z squared would be 13. And notice that sums up to 13, 11 is 24, and 7 is the 31 that you see right there, right? So this 31 would be x squared plus y squared plus z squared, which is part of this identity, which you can find this by hand if you want to. It's kind of tedious. There's 9 outputs when you square a trinomial squared. It gives you 9 terms, but you get products of 2 in here. And so now, and the rest of this all works out. You can see this would be 2. You factor the 2 out of all 3 of these terms, and you get 2 root 7 root 11 right here, and so on. So you can see these assignments for x, y, and z fulfill this algebraic identity exactly, okay? And so what we would get right here is that this would be equal to the square root, and then we'll have the square root of 7 plus the square root of 11 plus the square root of 13 quantity squared. And that's always good news when you get something like that, because squaring and square rooting are inverse operations. And so the final answer on this will just be the square root of 7 plus square root of 11 plus square root of 13. And that's fairly neat. I like this one, because often when you see this type of problem, it's a fairly common problem type. You're anticipating an integer solution. But if you take a look at this at the beginning, you go, what? There's no way this could be an integer. You can't even fathom that possibility. And so all you do is, all I did at least was just go through all of this and then recall this algebraic identity. And this was like a week's worth of, seriously, when you get to this point here, you go, what do you do? Then you realize you have to square a trinomial, not a binomial. Here, this is a binomial squared. You get this. You think maybe there's a possibility to fit it, but there's no fit that I can see. And so, but if you square a trinomial, you do get a fit. And this is the solution, folks. Hope you all enjoyed.